Okay, so in class today, we showed that any finite intersection of open sets in a metric space is again going to be open, but we wanted to show with this example that it's not true that arbitrary intersections of open sets are open. So we're trying to show that that arbitrary intersections of open sets then are not necessarily open. And we started to give this example. Here I just want to give a few extra details. And well, the example went like this. We take x to be equal to the real line with its usual Euclidean metric, and we let v sub n for each positive integer n be the open interval minus 1 over n to 1 over n. So here's the picture of v sub n here, and you might notice that v sub n is in fact the 1 over n neighborhood about 0. So, because each v sub n is the 1 over n neighborhood about 0, we know that each of these v sub n's is open. Because in theorem 2.19, we proved that in any metric space, any epsilon neighborhood is open. Okay, so what does that mean? We've got a collection v sub n of open subsets of R, and now let's look at the intersection of all these v sub n's. And, well, if we intersect all these v sub n's, what we're just going to get is the singleton set 0. I'm going to give the details of how to show that in a second, but let's notice first that this intersection, which is 0, is not open. Alright, so to see that, what will we do? Well, what we do is, well, for let x be a point in our set here. In other words, let x equal 0, and if this singleton set here were open, then we would be able to find an epsilon neighborhood about x contained in the singleton set 0. But in fact, then, for any epsilon bigger than 0, the epsilon neighborhood about 0, well, that just looks like minus epsilon epsilon, is not going to be contained in 0, obviously. All right, here is the singleton set 0, and if we took any one of these epsilon neighborhoods about it, it would look like minus epsilon epsilon, and that obviously is not contained in the singleton set 0. Okay, so this is enough to show that the singleton set 0 is not open. So this shows that our singleton set 0 is not open. Okay, well, the other thing that I wanted to check in detail in this video was I wanted to show that in fact this intersection here really is the singleton set 0. So let's do that now. Okay, so we claim that the intersection of all these sets minus 1 over n, 1 over n is equal to 0. Well, clearly, zero lies in this intersection. After all, 0 lies between minus 1 over n and 1 over n for any n, so 0 is in the intersection of all of these sets. All right, now, so to show the reverse containment, so at this point we have that the intersection is contained in the singleton set. Rather, at this point we have that the singleton set 0 is contained in the intersection. Now we want to show the reverse containment, that the intersection is contained in the singleton set 0. We give a sort of contrapositive argument here. So what do? On the other hand, we suppose that x is a real number with x not equal to 0. Well, we're going to show that x is not in the intersection. Well, then, by the Archimedean property, we know that there must be some positive integer k such that 1 over k is less than the absolute value of x, and therefore that means that x is not in the set minus 1 over k, 1 over k, right? If this is true, then x is either bigger than 1 over k or it's less than minus 1 over k, and so we can conclude that x is not in, I should have written, x is not in this set here, which is v sub k, and therefore certainly x is not in the intersection of all the minus 1 over n, 1 over n's. If x were in that intersection, in particular, it would be in this interval here, and it's not. So we showed that if x is not 0, x is not in the intersection, so if x is in the intersection, contrapositive says x must be 0. So any element in the intersection is 0. In other words, any element in this set is in this set. And we already showed that any element in this set, namely 0, is in this set here. So that's all we needed to prove, and we are done.